Hi, welcome back. This is going to be the ninth lecture on linear maps. Today we are going to continue with the matrix representation of a linear map, provided we are given ordered basis on the domain as well as the codomain. Right. So I would like to talk about one theoretical example. After that, today's lecture will be mainly theory because we had already done about 10 examples in the last lecture. That's quite a lot. Yeah. So let us start sharing the screen and start the work. All right. So let us look at one example now. This is, I think, 11th or 12th anyway, but this is the first example of today. Let V, W be finite-dimensional vector spaces, and let F from V to W be a linear isomorphism. Okay. Then suppose I choose a basis V1, V2, Vn ordered basis of V, right? Then I would like to talk about an ordered basis for W, but I can be slightly smarter. Remember, if it's a linear isomorphism, okay, then it's 1-1 linear map. Therefore, it's 1-1 linear map. We'll look at the set f of V1 to f of Vn. Okay, this will be linearly independent, right? But since it's a linear isomorphism, dimension of V and dimension W are the same. And therefore, in W, I have n linearly independent vectors. That means this must be a basis for W. I'm just giving a quick proof for this, but we had already seen if F is a linear isomorphism of from V on to W, then F takes a basis of V to a basis of W. We had already seen that. We had given a direct proof for that. Okay. And even that proof works in infinite dimensional cases. But anyway, so do you understand this? So I'm not going to take any arbitrary ordered basis for W. I am going to take this as the basis for W, namely B dash. So this is a basis of W. You understand this? Okay. This teaches a trick. What is the trick? I will come to that in a minute. Okay. Now let us take this basis. Now I want to know what is the matrix representation of F with respect to the basis B and B dash. So what is the first column? First column of this matrix is look at F of B1 and express it in terms of, call it W1 to Wn. Okay, as a linear combination of this basis vectors from W dash. But that's going to be 1 times W1 plus 0 times W2 plus 0 times Wn. There is the first column is going to be 1, 0, 0, 0, 0. And what will be F of B2? F of V2 will be W2. Therefore, it's going to be 0 W1 plus 1 W2 and so on plus 0 Wn. Therefore, that's going to be 0, 1, 0, 0, 0. Right? Now, let's look at the nth case. F of Vn will be Wn. Therefore, that's going to be 0, 0, 0, 1. So, you can see it's the identity matrix n cross n. You see that? Had I chosen some other basis B dash for W, I may not get this pretty matrix. I got a very simple looking matrix, namely the identity matrix. Right? Therefore, any linear isomorphism, if I choose my basis properly of the domain and take its image, that will be a basis for the codomain. And with respect to this two bases, ordered basis, the matrix is going to be identity matrix. This is a trick. The trick is, when suppose I have a linear map from V to W, okay, I want to look at a matrix representation. So for computational reasons, I would like this matrix, okay, to be in very simple form, as simple as possible, with so many zeros or some kind of pretty looking matrix size I would like to have. What is the trick? The trick is choose basis of V and W suitably. Here, what did I do? I I took any arbitrary basis of V, but then I chose my basis of W suitably, namely the image of the basis of V under F. You understand this? Pause, review, and proceed. Just to make sure you understand, let me do another example. These are all theoretical examples, but when you are going for higher studies in mathematics, you will appreciate, okay, the reason. Now suppose F is again a linear map, but this is 1 1, may not be on 2. So what do you think I will do? If V equal to V1 to Vm is a basis of V, then I know if it is 1 1, we already know dimension of V must be less than or equal to dimension of W, right? Now if I look, since this is a 1 1, let us look at the set F of V1, F of Vn, that's going to be linearly independent in W, right? Therefore, I can say this M, sorry, not N, okay? Linear independent. Now let us call this M and N, okay? Then I can extend it to a base of W that we know, right? So I can add some vectors F of V1, F of Vm, Wm plus 1, etc. Wn, okay? Therefore, this becomes a basis. This is an ordered basis of W now. I notice that I keep the same order. V1, V2, Vm, F of V1, F of Vm will be the first M vectors of the new basis for W. Then I don't care what happens to Wm plus 1 to Wn. Just choose. Okay, I don't care. But the first M vectors should be in proper order for what you want to do. Now, as earlier, what will you do? The first column vector will be start with V1, look at its image, that is 1, but this is a linear independent, therefore it's going to be 1, 0, 0, 0. This is at the mth place, and this is the nth place, this is 0. Second will be 0, 1, 0, and sorry, 0, 1. And mth place will be 0, 0, 1 here, 0, 0, etc. here. Okay, this will be 0. You understand? Now, you follow that? That's it. Okay, because what should be the matrix? The matrix should be of type n cross m. So this is the f of v1, f of v2, f of vm. Is it clear? So this is nothing like I of m cross m, and then this is a zero matrix of what size? N minus m. This is m cross m. N minus m cross. How many are there? M. That's it. Okay, this is something like a block matrix. This is called a block matrix. Something went wrong with the Zoom, so I don't know when it really crashed. Anyway, I may have to again do it earlier necessary. Let's see that. Okay, so let me share the screen. So now let us assume this is on to, right? Now I have to start with the basis of ordered base of B and ordered base of W. Here again we know that this means this is on to, that means dimension of V is greater than or equal to dimension of W. So what we do is we start with B dash now. Start with any ordered basis W1 to Wm. Okay, this is any ordered basis of W, right? Now let V1, V2, Vm be said that f of Vi be Wi for 1 less than equal to I less than equal to M. Okay, then it is easy to check. We had already done such things earlier, so I am just leaving this. V1 to Vm is linearly independent because summation Ci Vi is 0. Therefore, f of Vi this will be 0, but this will be Ci f of Vi, but these are all Wi. That's equal to 0. That means Ci's are 0. Okay, I quickly went through the proof for you. All right. Now what do? I extend V1 V2 Vm to Vm plus 1 Vm plus 2 to Vn. Okay, a basis of ordered basis of V now. Again notice that V1 V2 Vm I keep the same order such that f of V1 is W1, f of V2 is W2, f of Vm is W1. Yeah, and this is the ordered base of W. Okay. Now let's look at what is f of V1. F of V1 is V1. Now what is the type of the matrix? Notice that this is a matrix of type M cross N, right? Where N is the dimension of V and M is the dimension of thing. So this is going to be 1, 0, 0 up to M. You understand? Next will be 0, 1, 0 and next will be 0, 0, 1. After that, what will I do to these things? I'll map them to 0, 0. Okay. But I have to be slightly more careful, but that doesn't matter. So this is not any extension, but I use rank nullity to compute this as a basis of the kernel. Okay, I was not careful enough because this is reminiscent of our proof of rank nullity theorem. So I do not extend V1, V2, M to a base of W. What I do is, so let me repeat. So I have V1, V2, Vm. This is linearly independent in V. Then let us look at kernel of F. What is the dimension? That will be kernel dimension n minus m. So choose a base U1, U2, UK. Call this as a K. This is the basis for ordered basis of kernel. Okay, you understand that? Okay. By rank nullity theorem, we know then V1 to Vm, U1 to UK. This is a basis, ordered basis of V. Right? Therefore, if I look at the image, you can see this will be going to this, but f of u1 will be 0, 0, f of u2 will be 0, 0, f of uk will be, this is f of u1, this is f of uk. Okay, this is, sorry, f of u1. Okay, that's it. And f of u2, let me write carefully so that my handwriting is, and f of u1, and this is f of uk. That's it. So this matrix is identity M cross M, and this is a zero matrix. And how many columns? Yeah, M rows and K columns. This is zero matrix. So again, we found a pretty looking matrix representation. Okay. Pause, review, proceed. You understood the trouble here? I could not extend to any basis because I do not know what will be f of Vm plus 1 here. But if I choose this Vm plus 1, Vm plus 2, Vm as the basis for the kernel, then I'm happy. Then I can make it. See? You understand? So I have to be careful in choosing the basis so that I can arrive at a pretty looking matrix. This is the very important trick you have to learn if you want to go higher in linear algebra. So please review all these three examples. Take some time. They are a little abstract, but if you are mathematically oriented, algebraic interest, then you will love this. Okay, very good. Now we will go back to theory now. Okay, so I want to make the first some observation. Suppose f is from b to w, and I choose an ordered basis b and b dash with the stamp notation. Okay, v1 to vm and w1 to wn, etc. Okay, I will not keep repeating. Okay, now what I want to do, I want to drop, make the notation somewhat simpler. See, if a vector v is given in v, then b, what is this? This is the coordinate vector b, right? That is b, you write as a linear combination of v1 to vm, call it x1 v1, xm vm. Then this is the column vector x1 x2 xm. So this hereafter I will write it as simply v, because the b is fixed, so I'm not going to change for the time being. And similarly for w, instead of wb dash, I will write it simply as w. So naturally, this denotes the matrix. This stands for the matrix with respect to the basis. Okay, this is a simpler notation because b and b dash are fixed for this discussion. So there is no point in writing them, making our life more complicated. Is it okay? Very good. Now, what we want to do is something very interesting. This is the theorem I want to prove. So keep the notation as above. Okay. Now let's look at f of v. For v in v, let us look at f of v. This is a vector in w, therefore I can look at its coordinate representation. Okay. It is b dash, but I am not, as I said here, I am not going to write b dash here. The suffix b dash I am not writing. This is, now write this as a matrix. This matrix, call it a A. This is a matrix where this is in M, n cross M of R, if where R is a field. This I claim is A times this. Do not get lost. See, if I write f of v as y1 w1 plus yn wn, this side is y1 to yn, and this is matrix a11 a1 m an1 anm. Okay, and v will be, if I write x as x1 v1 plus x m v m, this is n, and this, okay, x1 x2 xm, this is what it says. Okay, you understand this? So in other words, I have a linear map f from v to w. Now v, using the coordinate maps, I have a linear isomorphism of this with Rm. I have a linear isomorphism of this with Rn. This is what we called phi b and phi b dash, using the coordinate, right? Now I have a linear map A, because any given any matrix, we know it gives rise to, this is an n cross n matrix. We know it gives rise to a linear map from Rm to Rn. Okay, and then that is, and this matrix is unique. Okay, satisfying, call it 1. What does that mean? What is this A? This A is just f. So f of v equal to f into v. Very pretty nice looking, right? Okay, right. So this is a matrix. I claim this matrix is unique because notice that this is a vector where in Rn. This is a vector in Rm. This is a matrix in whatever I wrote. This is going to be a matrix in n cross m to R. You understand? So if you give me some other matrix B which satisfies this condition, namely f of v equal to b times this, then I claim this b is nothing other than f. That is our A now. I decided to call it A. Okay. Please understand. Do not get confused because too much of notation at, okay, to understand the statement of the theorem. Okay. Don't worry about the proof. Most often students are worried about the proof and remembering them. Do not. Most important thing, understand the statement, what it tries to say, what is the significance of the theorem. Then you look at the proof. Once you understand this, you will see the proof becomes easier actually, because you know what you want to prove. Okay. This is a trivial. There is nothing for us to prove. It is essentially we have already seen. So let me just recall. So this is a recall. Suppose A belong to n cross m of R, then I have a linear map from Rm to Rn, namely x going to, this is a column vector, this goes to the product of these matrices, right? This is a linear map you had already seen. I just now said that, right? The most important thing we have seen is what is A of Vi. Let E1, E2, Em be the standard, okay, standard basis of Rm with column vectors, of course. This is column. Okay, this is nothing other than the ith column of A, right? Because A11, A1I, A1N, and AN1, ANI, AN, it is M, AN, acting on 0, 0, 1, 0, this is ith place. Multiply, when I multiply this, I will pick up only A1I. When I multiply the second one, A2I. When I multiply this with N, I am going to get ANI. You understand? Okay. All right. So this is nothing other than A11, sorry, A1I, A2I, NI. Okay. Right. Keep this in mind. Now you can ask what is then A of X? Suppose X equal to X1 Xm. This I can write as X1 E1 plus Xm Em. Therefore, A of X is nothing other than, no, notice that matrix multiplication is linear. We had already seen X1 E1 plus Xm Em, but this is X1 times first column. This is the first column C1. This ith column Ci. X2 times C2 and so on. Xm times Cm. Okay. We had already seen under the linear maps, but knowing the students usually they may not remember, so I am recalling the proof. Is that clear? Yeah. Pause, review, and proceed. Now we want to use it. Let us look at the matrix F. What is the column? We had already seen the first column is F of V1. This is the first column. And F of Vm. You understood this? Okay, this is in a matrix. This will be A11, A21, and AN1, and so on. A1n, A2n, and AN, ANN. Yeah, that's how we construct the matrix. You understand that? Write F of V1, write it as a column vector in my terms of W1 to Wn. That's what we are. You understand this? Sure? No doubt? Okay. Now suppose I have V. Then V is what? V is going to be some xi Vi. I equal to 1 to m. You understand? Therefore, from whatever I said, okay, what I have to look at what is f of V. F of V is going to be xi f of Vi. Yes, because of linearity. Yeah. Okay. Now, what do you think I have done? Notice that what you want to prove. We want to prove look at f of b, its coordinate vector in terms of the basis b dash is what I have to do. Do you think I got it? Okay. This is nothing other than, okay. So let us look at, let us go slow in case you are getting overwhelmed with the notation. This is f of v1, f of vm. Okay, this is your matrix. These are all column vectors. Multiply by x1 x m. So how will I multiply? Exactly this. Therefore, it's f of v. You understood that? Okay. So this is a vector, right? So this vector equal to f of v. Therefore, the column vectors will be equal. Therefore, f of v equal to this matrix F into the matrix V. Okay, because when I writing, then what do I have to do? I will write this as xi f of vi. That's okay. You follow that. I hope all of you are following. Sure. Okay. So this is a matrix. I want to look at f of v. What will be f of v? F of v is xi v f of vi, but that's going to be x1 into a11, a21, an1, and so on. But what is this? This is with respect to the basis, right? So what I have done with respect to the basis, b dash. Yeah. Therefore, I have written f of b as a coordinate vector in terms of w1 to wn. Okay. Pause. Review. Proceed. Okay. And why it is unique? Now I have to check uniqueness, right? Suppose I have f of v, this column vector equal to some v of v, right? Then take v equal to vi. Then what will this be? This will be f of vi, right? But this will be v of vi. That is the ith column of b. But this by construction, this is the ith column of a. Therefore, ith column of a equal to ith column of b. This is true for every I. Therefore, a equal to b. Okay. Right. So let us recall. I hope you will review. Please review again. Okay. Do not simply want to believe me and assume. Okay. It's worth paying attention. Go back. So let us recall what we have done. With respect to the notation, I have base is ordered base b and b dash. Then what we said is, let us look at f of v for any v. This is a column vector in Rn. This column vector is, look at this matrix of f, that is a vector of type n cross m acting on the vector v. Where, right? This is a vector in Rm. Okay, this is what you have done. Okay, keep this in mind. This is exactly one. This is going to play an important role. Now let us look at what you have done. I suppose LBW, we know this is a vector space. Do you remember that? We actually computed the dimension. Okay, this dimension is, okay, that is m times n. Okay, now I have a map phi from L of VW to matrices m cross n R. Okay, how is this given? Give me a linear map and send it to the matrix representation of this linear map. Okay, I want to know, since notice that this is a vector space of dimension mn, this is also a vector space of dimension mn, right? So natural thing I would like to know is whether it is going to be a linear map, whether pi is a linear map. Second will be I'll become greedy. Since both have the same dimension, I may be tempted to ask whether this actually is a linear isomorphism. Yes, these are all very natural expectations, right? So let us do that. So what is that I want to check? So phi of f plus g, whether it is equal to phi of f plus phi of g. This is what I have to check. But what is phi of f plus g? Let us look at the matrix representation of f plus g. I want to know that is same as the sum of these two matrices. Do you understand? Do not play with symbols. Try to understand the meaning. Phi of f plus g is the matrix of f plus g, linear map. Okay. Now phi of f is again a matrix. Phi of g is again a matrix. So what is the vector addition here? It is an addition of matrices. Right? This is addition of linear maps. You understand? So we want to know what this. Right? Now notice that the representation, matrix representation is unique. Just now we saw that. Right? Okay. Anyway, I want to say whether these two linear maps are same. So to check, what is that I have to do? I have to check, start with any vector b in V. Okay. Right. Let us look at this one, b in Rm. Right. Notice that b going to this is an isomorphism of b to Rm. And similarly, w going to this is an isomorphism w to Rn. These, okay. Under coordinate maps, we had already seen this ordered based on coordinate maps episode. We had already seen these are all linear isomorphism. Okay, right. So it's enough if I check this matrix acting on the column vector V is same as this matrix acting on the column vector V. Notice that I am writing all these things. Again, you should understand what is. Do not, okay, unfortunately, many students just manipulate symbols. You should understand. This is a matrix, these additional matrices, this is a matrix. What is this? This is a product of matrices. Product of matrices, you know, is a distributive. This is same as F times this and the product of these two matrices. You understand this? This side. Okay. What is this side? This side, just by definition, we have seen is nothing other than F plus G acting on B. This is by 1. What is 1? F of B is F acting on B. You understand? Using this, I have this. But what is F plus GB? That is F of B plus G of B. This is by definition of addition of linear maps. Okay. It's fun if you understand mathematics rather than symbolic manipulation. You understand this? But what is this? That we have seen coordinate map is a linear isomorphism. Therefore, this is linear map in particular. So these two are equal. Okay. So this is additive. Phi is respects addition. Also, or preserves addition, or one or simply says additive. It's an additive map. Okay. Shall I go through it again? Anyway, you can always pause and review and proceed, right? In a classroom, I have to go back. In video recording, I don't know to. Okay, you can go back, right? You can just pause the video, go back and understand. Okay, please understand the mathematics involved. Do not accept, blindly follow symbolic manipulation. And a similar thing is true for with respect to the other one. What is that I have to do? Phi of TF, whether I have to say whether it's T of phi of F. Again, it's the same thing. So I have to act on any V Okay, and what is this? This is TF. So it's enough we check whether this is true, right? Okay, you understand? But this, by equation 1, this is TF acting on V and the coordinate map. Are you sure you are understanding? Yeah? Okay, now let's look at what is this one. This is T. This is the product of two linear maps. Okay, you understand? This is T. I don't want to do anything. T times. This is a scalar. This is a matrix, and this is another matrix. This is a product of matrices with a scalar. Okay, this is right side is understood. Now I will work on the left side. TF acting on V by okay by one. This is by one. Okay, what is one? Let me again recall. F of V equal to matrix F into the coordinate V. All right. So this is linear map acting on this. This is the right side. This is equal to this side. Yeah. But what is this by definition? Now remember, coordinate map is a linear map. Therefore, this is same as T times F of V. But again by 1, this is T times F into V. This is by 1. Therefore, these two are equal. Therefore, phi preserves scalar multiplication. Therefore, phi is a linear map. Okay. Pause, review, and proceed. Okay. Now the next question is phi 1 1. Since it's a linear map, to check it's 1 1, what all I have to do is phi of 0. Okay, if the only kernel of phi is 0. That means if phi of f is 0, notice that what is this? F is in this is a linear 0 map, implies f is 0. Right? Okay. So this 0 is same as saying this is 0, that is phi of f. Okay. What is phi of f? That's a matrix acting on V is 0 matrix acting on V for acting on the scalar, the coordinates V. Are you following? Don't get confused. If you are a second year BSc student, it is slightly tough. I know that. That's why I'm going very slow. Is phi of f equal to 0? This is what? This is a matrix. This equal to 0 is a 0 matrix, right? I want to say the linear map is 0. You follow that? Okay. If phi of f equal to 0, what does that mean? What is phi of f? Phi of f is this. This matrix is 0. Yeah, right. So what I have shown now? I want to say f is 0 then. Therefore, I have shown f of v is into v, but this is 0. You understand this? Right. Okay. Now, why should it say f is 0? So I want to claim f is 0. That is very easy because let us look at v equal to vi, the ordered basis. Then what will be f of vi? That will be 0 vector. That means f maps each basic vector vi to 0. That means f is 0 map. Okay. And the last one, phi is onto. That is easy. Suppose I have a matrix A in, right? I want to define f in L of BW so that f equal to A. Okay, I have to find such an f. That's very easy. Why? Look at, I have to define f of vi. I will simply define f of vi in such a way that the coordinates of that is the ith coordinate, that is a1 I of w1 plus a, let me write, yeah, ni of wn. Please understand, just you should think and then write. What do I want? And the matrix of f should be a. But what is a? Ith column is going to be the image of f of vi, right? If such a map existed, f of vi, the coordinate of f of vi must be ith column of a. What is ith column of a? A1i, A2i, Ani. But what does it actually represent? This represent f of vi, if I write as a linear combination of w into wn, this is what I should get. So we define now. You understand this? I have to find a linear map f. I am going to define its action only on the basic vectors. Okay, are you following? So f of vi equal to this. Then extend this. Okay, then there exists, we know, a unique linear map f in L of vw, so that f of vi is this. So that f of vi equal to a1i w1 etc. a-ni wn etc. So that is the linear map, and by very construction the matrix representation of f is precisely a. Yeah, please follow this. So I will end this lecture with a typical example so that you should appreciate this. So all these are very abstract theory. Okay, it will be always good idea to have one or two more friends of yours sit at each PRP, review and discuss. Mathematics is fun. If you discuss, each one of you will help other to learn better. Okay, so don't try to make it solo. Right, anyway, come back. Now let us look at, there are two things. Our LVW, do you remember? We showed it's m n dimensional, and by looking at showing some vectors Fij here as a basis. What was Fij? It mapped Vr to be 0 if r is not equal to I, and mapped to Wj if r equal to I. That is f of Vi is Wj. Fij of Vi is Wj. That's all. The rest are all go to 0. Okay, keep this in mind. That's it. Right? Okay. So what does this? This Fij should correspond to some matrix in, right? What is this matrix? Naturally, that will be this collection of such matrices will form a basis, right? Okay. Again, we can immediately write it. What is this? So what is Fij does? So Fij of V1 will be 0, right? And so on. Fij of Vi equal to Wj, therefore it will be 1. Okay, this is ith column and this is the jth row. This is j, this is I, and then rest are 0. This is it. Therefore, this corresponds to the what we call E. I don't remember. I think called EJI. So it does not correspond to. Notice that we had already shown EIJ. EIJ is the matrix whose ijth entry is 1, otherwise 0. Right. All right. So you may be tempted to say Fij correspond to Eij, but it does not. Where does it correspond to? It corresponds to Eji. Why? Because where does Vi go? V1 will go to 0, V2 will go to 0, Vi will go to Wj. When I write Wj, it's going to be ith column. This must be ith column. But then 1 will appear in the jth row. Therefore, it is Ej1, Eji. Is that clear? I hope you appreciate this exercise. Nice example. Okay. So again, let us stop the lecture here. There is one more thing. I'll do it in the next lecture.